Okay, thank you all for coming. We are very happy to have Philine. We'll talk about his, no, her nice work on one-dimensional long-range Ising model. This is one of the, maybe the oldest critical phenomena that people, human beings ever studied. There are some recent nice progress. Okay, let's start.
So thanks very much, Junchen, for this introduction, and thank you for inviting me to speak here. So indeed, I'll be talking about a paper that we published this year, and also together with Dario Benedetti and Edo, who is one of the organizers, and Dalingo Massage. And there's also a longer version of this short letter upcoming, and hopefully done soon, in which we provide more explanation for the model that we proposed in this paper. So indeed, it's about the Ising model with long-range interactions, and then especially close to the point where we have a crossover to the short-range Ising model in one dimension. And there has been some description lacking, namely a weakly coupled field theoretic description that can be used to do systematic perturbation theory. And it's exactly this that we wanted to address in this letter, and we propose a model that can exactly provide such a description. So first, some motivation of why you would want to study long-range theories in any dimension. So we all know that the short-range Ising model, so the usual one with nearest neighbor interaction, is very well understood. It has been studied a lot, especially the critical phenomena that belong to it, using all kinds of methods perturbatively, but also non-perturbatively with the conformal bootstrap. But the long-range Ising model remains much more mysterious, and there hasn't been as much work on it so far. And in contrast to the short-range Ising model, where the critical behavior corresponds to a single fixed point, we now have a line of fixed points and parameterized by this interaction parameter S in any dimension. And this corresponds to a family of CFTs. I put here 1D, but D-dimensional CFTs. That was a typo. And so with one model, we can study an infinite family of CFTs. And this is very interesting in itself. So long-range models are non-local, meaning they don't have a conserved stress-energy tensor. And so this Ising model might be a natural starting point to study other non-local CFTs. It can be seen as maybe the easiest version of a non-local CFT. And examples are conformal defects or QFTs in ADS and other models. So this holds for any D and is a reason to study these models for any dimension, but the one-dimensional case is kind of special in this way.
Is it as an integer or
no, S is continuous, so it can be anything. Yeah, but we will take the D. In general, we take D to be integer. So in one dimension, it's maybe even more interesting because the short-range Ising model has no phase transition at finite temperature, but the long-range model has a second-order phase transition, or again, a whole line of fixed points, and we can study its critical phenomena. And this is because the Coleman-Mermin-Wagner theorem that forbids the existence of a phase transition for the short-range model does not apply for sufficiently long-range interactions, and we can avoid it by looking at the long-range model. So there is critical behavior for this parameter S being in between 0 and 1. And it's even possible to get an exact solution at S equals 1. And what we want to do here is to develop, or I want to present you a model that allows for systematic perturbation theory for S slightly smaller than 1 and close to this point. So, okay, I will first introduce the long-range Ising in general dimensions and explain some things about it that will further motivate why the 1D case is special and why no one had found this description before. And then I'll specify the one-dimensional case and explain a bit also about the history of what has been done for this model. And then I'll go on and present our description and provide you with some consistency checks so that you're hopefully convinced that this model is indeed the 1D long-range Ising. So here we have the Hamiltonian for the long-range Ising, which is very similar to the short-range case. But now, instead of having only the nearest neighbor interactions, we can have interactions over infinite distance. And we see that this parameter S appears here in the denominator, and I and J are the sides of the lattice that we sum over. And the sigmas are just spins up or down. And as I said before, we take D to be integer, but S can have any value between, well, it can have any value in principle. And we see that we find non-trivial critical behavior if it's in between D over 2 and some value S star, where S star is supposed to be located around the point where you go to the short range sector. So you would go to short range interactions after crossing S star. So S here parameterizes a family of non-local CFTs, but they are unitary, and we can use the ordinary conformal bootstrap techniques to study this critical behavior if we want to.
And before the alpha, for things smaller than the alpha? Or...
Yes, so for things smaller than the half, there is critical behavior, but it can be described by mean field theory. So this is trivial, the trivial part. Oh, so we have a range of values for S, and we can actually describe two different perturbative regimes for each of the endpoints of this value. So the first one is for small s, so close to D over 2, where it's just mean fields. We can describe it by a mean field theory. So we can start from D over 2 and perturb it by a small parameter epsilon. And then we can write the action as a generalized free field phi plus some interaction, some local interaction that is a phi to the fourth interaction with parameter lambda. And this non-local kinetic term has some profound implications. So first of all, it leads to the fact that phi has a protected dimension, because this non-local kinetic term cannot be renormalized by any of these local interactions that we add. And this leads to the fact that phi will always have scaling dimension d minus s over 2, no matter what the value of epsilon is. And due to the equations of motion, we find that also another operator has protected dimensions, and this will be phi cubed. And we see that if we add these two dimensions, we find the space-time dimension of the model D, and they form a shadow pair of operators. And you can again see this by looking at the non-local equation of motion from this action. Now, on the other side, we can have a different description. So as I said, if we're close to this value S star, we expect to go towards the short range Ising model behavior. And we can perturb from that side. So we can start at S star and go a little bit below it with a value delta. And here delta sigma star means the scaling dimension of the spin field in the short range Ising model. So at first it was thought for a long time that the behavior for delta goes to 0 should just be the short range Ising model. Then later on it was found that this was not the exact correct solution, and it was a paper by Miguel Paulus, Slava Ryzhkov, Bernardo Zan, and Balt van Rees that actually showed that the correct behavior is not just a short-range Ising model, but coupled to a generalized free field. So here we have a generalized free field chi that gives you the non-local kinetic term again. And this is the short-range Ising action, and we couple the chi to the spin field sigma by some parameter g. And we find that also here the operators have protected dimensions. So chi has delta plus s over 2 and sigma has the opposite. And when we add the two, we again find that they're a shadow pair of operators. And this is good because it means that we have now two different perturbative descriptions, and we can match the operators to each other. And we can identify operators on the mean field theory side, the phi to the fourth side, to the operators that we have on the short-range Ising model. And so we find a description that is continuous, possibly continuous along all S. Yes.
How do you cook up the interaction like the term with the ratio? Like you have the d minus s and d plus s on one side, and the other side the different signs. How do you know that this is the correct interaction that you should put?
Yeah, so you can again just look at the equations of motion that follow from this action. Here you see that you have a d plus s, and here you have the d minus s, and this accounts for the change in sign of also of the dimensions. So here the generalized free field has the minus sign, and here it has the plus sign.
Yeah.
So in this way you can.
Okay, so you know, because you know the things that you want in the end from the equation of motion, and then you look up the action that you have the correct.
Yeah, so I think the way they found the action was they first looked at, they first thought it was just the short-range Ising part, but then there's some mismatch between operators. There's some operators that are supposed to be there on the long-range Ising side that are not on the short-range Ising side. So they needed to add another part to account for these operators and make sure that some of them get eaten by the right operators in order to make the crossover to the short-range Ising side. And that's why they came up with this idea that you have to add this generalized free field. And then from that, it also, yeah, I don't know, you can say, okay, you know that these operators need to have these scaling dimensions, and in order to make it match, you needed to add this generalized free field. Yeah. Okay, any other questions so far?
I have a very naive question.
Sure.
So in the short-range Ising plus GFF, it seems that you can integrate the chi completely, right? If you are doing the field integration, because chi is just a Gaussian field, and you, in the end, you will get a Gaussian interaction term on sigma. And what is this interaction term? Does it correspond to the this interaction in the mean field side?
I'm not sure if I completely. So if you mean if you integrate out chi?
Yeah, it can be Gaussian integration of the chi, right?
Yes, I think you would get the left-hand side term.
You just get this an effective phi to the fourth action for sigma.
No, the connecting term.
Just this one?
Yeah, I think. Well, you can treat it as a perturbation around short-range model. That's what SAC
Sure, yeah.
original did. But I think this interpretation is a bit better. It gives you more field content and explains some mysterious non-matching.
Yeah, I thought if you would do this, so SAC's picture, that you then have some operator mismatch with if you do this crossover. So yeah, if you do that, you don't get the exact correct description. Yeah, thank you. Okay, so we see that we have our line of long-range fixed points here, and we can approach it from two ways. So either from the short-range Ising side, or from the mean field theory side by a flow of phi to the fourth. And this is a very nice picture that should hold in any D. However, in 1D, this picture does not work because we don't have a short-range Ising CFT that we can use as a starting point to perturb from. So the phi to the fourth, the mean field theory picture, this holds to any D, and also in 1D, you can describe your Ising model around S equals a half in this way. But the short-range Ising side does not work, and we need to find an alternative for this part. And this was the motivation to pick up this problem and to look at how we can find an equivalent picture to this picture that was found by these authors. So let us now have a look at the 1D long-range Ising. So we really just have a line of spins that can point either up or down. And we see that we can describe it as some spins, some up spins for a while. Then you have a block of spins that point down, and then you have a flip where your spins start pointing up again, and this repeats over the whole distance of your chain. And the Hamiltonian, okay, I already wrote it before, this is now specific for 1D. And you could, in principle, add some local terms to it that has been done in historical papers. So that's why I wrote local terms, but I want to be a bit vague about the exact nature of these terms. So for S between 0 and 1, this model has a phase transition for some critical temperature that is larger than 0. But for S bigger than 1, so if you go towards the Ising regime, it has no phase transition. And this is also consistent with what you would expect from the short range 1D Ising model. So in principle, there is no conceptual issue about going to the short range Ising that point, but we know that at t equals to 0, the short range Ising is just some tq of t with a ground state plus or minus 1, and the spin field sigma is a topological operator with scaling dimension equal to 0. So this is what we also expect for the long-range Ising model as we approach s equals 1, that we have one operator with dimension 0 and a crossover at 1. And now there's two problems that we face. One is to understand the theory at exactly s equals to 1, and the other one is to do perturbation theory for slightly below. And we'll see that these are actually, both theories have different issues. So at exactly s equals to 1, the picture is maybe a bit clearer, but there's different questions that we need to answer.
So does the critical temperature goes to 0 like continuously as you approach s equal to 1? You have a TC.
Yes,
TC
exactly. Yes.
do not exist for s bigger than 1. So
Yes. Yeah.
so it goes continuously.
I think I don't know. I think there's something that some discontinuity that happens as you s is exactly equals to 1.
I see.
Yeah, it's not
Thank you.
now some historic things. Okay, I forgot the reference has fallen off, but okay. So the historic picture of the 1D long-range Ising is now that you can look at all these spins and you can put an alternative description in terms of domain walls where the spin flips. So we don't have to keep track of all the individual spins. We only need to look at the points where they flip from up to down, and we can define a kink operator such that it's +1 if it flips from up to down, and it's -1 if we flip from down to up, and it's 0 everywhere where we don't have a spin flip. So now we have a picture in terms of these, well, just these lines. We can forget about the spins below, and we can write our Hamiltonian in terms of this kink operator instead of the spin field sigma. And it was found by Anderson and Yuval and Hamann that these domain walls, you can see them as dilute at low temperature, so below the critical temperature, and you can rewrite the 1D long-range Ising model as a Coulomb gas of these kink operators. And this description is what they wrote down. So instead of having this Hamiltonian here, we now write it in terms of Qi and Qj times some potential that depends on the location of the domain walls. And this was a picture that they wrote down for initially Anderson and Yuval for exactly s equals to 1. And it was extended by Kosterlitz to go to S slightly below 1. And he wrote down the following partition function, where you again, this -1 over here is the kink operators that we just saw. And this potential V has the following form where Xi and Xj are now the locations of the domain walls that in between spin flips. And the parameter G here is the fugacity, and A is some lattice cutoff that you can define, and J is the interaction strength. So this was a very nice model, and now for S smaller than 1, he did some renormalization group theory, so he was able to derive some beta functions in a very primordial, pre-Wilsonian kind of way. So he found the following renormalization group equations for both G and J, and we see the picture on the right. And the fixed points, for G, he found that the fixed point had to be of order square root of delta, and for J, the fixed point was around 1 plus some order delta correction. And delta is here defined as 1 minus S, so this is for really close, S close to 1. So from this beta functions, you can see that there's 2 Z2 even operators. So these are the, well, we will call them O plus and minus, with anomalous, with scaling dimension 1 plus 2 square root or square root of 2 delta at the fixed point. And if we compare this with the mean field theory picture of the 1D long-range Ising, we see that these 2 operators can be identified with either phi squared or phi to the 4th. So this is to give you an idea of what they are. So this was already found by Kosterlitz in 73. And okay, you can think, well, this is it. This is a valid weakly coupled description, and we're kind of done. But it turns out that it's rather cumbersome to work in this description. It's difficult to get any predictions to higher order than what he has found here. And we wanted to come up with really a field theoretic way to describe this same behavior.
So sorry, so delta equals 1/2, it's the perturbative GFF.
Sorry, that's what type of?
Delta equals to 1/2, it's the comparison with the phi to the 4th perturbative regime, right?
Yeah, exactly. If you go towards, if you go towards 1/2, yes. Yeah, or you push epsilon a bit higher than, you meet it in the middle.
Okay. I see.
So our goal would be to now, well, first of all, our goal would be to find a theory that gives us the same beta functions and the same RG equations as Kosterlitz found. And we also want to find operators that, these 2 operators that have the same scaling dimension. So this is to really make a connection with the picture of Kosterlitz, Anderson, and Yuval. So the AYK model, as we dubbed it for short. And second of all, we also want to make the connection to the full phi to the 4th theory on the other side, so that we really have a match between for all values of S. And then, okay, later on we will do some more checks, but let me leave that for.
Sorry, what are these 2 pictures?
Yes, so these 2 pictures are the flows that are described by these renormalization group equations, and above is the one for S smaller than 1, and below is the one for S exactly equal to 1. And the x-axis here is roughly J, and the y-axis is the value of G. Okay, so for our model, the starting point will be a compact generalized free field phi with scaling dimension that is negative. So it's minus delta over 2, and it goes to 0 as delta equals 0. And okay, it has some periodicity because we compactify it. And for this theory, the well-defined operators that we use as our building blocks will be derivatives of the field phi and vertex operators that are just exponentials of this phi times some parameter b. And it's especially important to notice that phi itself is not a well-defined operator in this theory. So, for example, it doesn't respect shift symmetry, and hence we need to exclude it from the spectrum. So all the operators that we have will be built from derivatives of phi and vertex operators, but not phi itself. And this is good because since phi has a negative scaling dimension, we don't want it in the spectrum because we are looking for a unitary or reflection positive theory. And by taking it out, we obtain exactly that. So now you can complain a bit because it's okay. GFF with negative dimension, is this well defined? What does this mean? Normally we don't look at these kind of theories, but it turns out that it is a well-known theory and has some other applications as well. So it's known as a fractional Gaussian field, where which is this H, which is defined as the fractional Laplacian times some white noise distribution. And the fractional Laplacian is exactly this non-local kinetic term that we also saw in the perturbative descriptions all the way in the beginning. So for these fractional Gaussian fields, you can define some parameter, which is called the Hurst parameter, H. And in our case, this will be equal to minus the dimension of phi, so it will be delta over 2. And if we put s equals to 1, then we find what we would usually call the GFF. So then everything is back to normal. And if we also specify to 1D, we have our Brownian motion that we are all familiar with. But for other s, for example, a Hurst parameter in between 0 and 1, we don't have Brownian motion anymore, but we have something that's called fractional Brownian motion. And this means that you still have a random walk, but now the different increments are not independent of each other, but can be dependent of the previous step that you took. This was introduced, or the name was given by Mandelbrot and Van Ness. And it has also applications in economics and fluid dynamics. And it's especially useful to describe interactions that have different scales and also some long-range interactions. So this is a whole set of literature that I was not familiar with before this project, but it exists and it shows that that you can define there is some more general notion of a GFF that includes negative scaling dimensions for the field. And it was also very good that this was proven to be reflection positive in 2018 by these people here. So with that, yes.
We usually see that negative dimensions is below unitarity bound. And...
Yeah. So in this case, it's okay because phi is not part of the spectrum. And anything you build from phi, like derivatives of phi and the vertex operators, will always have positive scaling dimension. So this is why it was important to exclude it. But as a starting point for a theory, it's still a well-defined quantum field theory. So now we had our GFF with the vertex operators, and you can show that this correlation functions of only vertex operators will produce exactly this exponential term that we saw before in the partition function of the AYK model. And this shows that you can reproduce this one for, especially you can show rigorously that this is the case for delta equals 0 and s equals exactly 1. And you can also make the connection for small delta if you expand it perturbatively. However, if you just take your vertex operators and you take a correlation function, it will normally take any ordering of the V's, and it will have a constraint that you have to have as many V plus as V minus, but the ordering can be arbitrary. You could have V plus plus plus, minus minus, etc. So we need to find a way to enforce this alternating pairs of V plus and V minus, because these are the ones that would correspond to the domain walls that have either up or down flip of your spin. So you cannot have two domain walls with the same sign because it doesn't correspond to the physics that we want to describe. So we need to find a way to enforce this configuration. And it was shown in, well, for the theory at s equals to 1, that you can do this by introducing matrices S plus minus that are just combinations of the Pauli matrices. So they take this form, and if you square them, they give 0. So now if instead of taking V plus V minus, you take sigma plus V plus and sigma minus V minus, you automatically enforce that if you have two pluses next to each other or two minuses, that it will be 0 because of this condition. So by perturbing or by perturbing our model with the sigma matrices, we find that we enforce the constraint that we can only have correlation functions of this type, and hence we'll perturb our GFF by this operator OG that has the following form. And now these terms are exactly the kink creation or annihilation operators. Any questions so far? Good. So, okay, this is one way, and this is very nice, but we saw that in the AYK model, we had two different couplings that were both tuned to reach the critical behavior. And this will give us 1, so we can add some OG with a parameter G, but we need to find a second one to find the full flow diagram that Kosterlitz found. And luckily, there is a second marginal operator that we can add to our theory and that we can perturb by, and this is what we call OH, and it's the derivative of phi. So this is a good operator that is in our spectrum times the third Pauli matrix sigma 3. And if we add both of these, then we find the full partition function of our model that we say is leads to the same IR CFT as the 1D long-range Ising model. So we have our two couplings, and it's interesting to see that if we add this model, this operator OH with this coupling H, normally you could also do this in other models, for example, the Kondo model, and you see that the role of this OH is to shift this B0 parameter that was in the definition of our vertex operators to some B that is B0 minus square root 2 of H. So you could use this to just set H to 0 and to just keep your B or your B0 running. But it turns out that if you want to properly renormalize the model, it's important to actually keep this this interaction term and to keep this perturbation in the full model. And instead, we will just set B0 to our favorite value, which is 1. And now if we take this full partition function and we expand it in small g, we find exactly the partition function of the AYK model, where we identify B squared with the interaction parameter J. So this is the proposal of our model. And with this model, we can now do perturbation theory, and we can check that we find the right beta functions for the AYK model. Okay, so let me go to the consistency checks, and then hopefully some more things about this model will become clear. So first, we want to match the RG equations. second, we want to check that the model has the same symmetries as the 1D long-range Ising. And we want to make sure also that the spectrum of operators matches with the mean field theory psi. And lastly, we want to check that the model indeed corresponds to a family of 1D CFDs. And this we'll do by checking with the analytic bootstrap and showing that it agrees with whatever we find in perturbation theory. Any questions so far? Good. Okay, so we can do the perturbation theory. We'll use conformal perturbation theory to compute the two beta functions for G and B squared or J. And we find the following answer and the following fixed points. So we see that we reproduce what Kosterlitz found, which was an ordered square root delta correction for G star. We were able to find what exactly this term is. And 1 minus an ordered delta correction for B squared. And again, we could easily go to figure out what exactly the form of this delta correction was. So we can also then compute the anomalous dimensions of these two Z2 even operators, delta plus and delta minus. And we find the answer that Kosterlitz found, plus some higher order corrections, delta over 4. And if we now compare with our model, we can also see what the field content is for this O plus of minus. And we find that they have to be some linear combination of the OH and the OG that perturb the GFF. And this linear combination will also get corrections as we go higher in delta, but in principle, it's given by OH plus or minus OG. Now for the symmetries of our model, we find the following results. So we have a Z2 symmetry. That is good because we need it in the 1D long-range Ising. And this one will send phi to minus phi, but it will also flip S plus and S minus, the two Pauli matrices, and it will send sigma 3 to minus, or S3 to minus S3. We also have parity symmetry, which is specific in 1D. Instead of the usual spin in 1D, operators can have some parity. And we also find an U1 symmetry in our model, but this U1 symmetry is not supposed to be there in the long-range Ising. So there's some things we can do. One is to just simply consider the U1 invariant sector, and this is in practice what we will do. But if you want to be more precise, you can also gauge this U1 symmetry and get to the proper operator content of the 1D long-range Ising model.
This U1 is the shift of phi.
Yeah, you can send phi to I alpha phi. This is also why phi, we can also not have phi in the spectrum if we restrict to the U1 invariant sector, that's also. Now, at S equals to 1, we find, we know the exact solution of the model. So this GFF with dimension of phi minus delta over 2, if you set delta to 0, it is just a free field with Neumann boundary, a free 2D scalar with Neumann boundary conditions. And this theory is exact and you can solve it. And in particular, you can find the exact spectrum because all scaling dimensions are just positive integers. And here is a table of which operators we expect to find, where this plus and minus denote the symmetry under parity or Z2. And we see that at delta equals 0, we have 2 operators. At delta equals 1, we have 2 with even parity and even Z2, and 1 odd parity 1, etc. And we can go on for how long you want. But it might be instructive to have a look at these first few operators that we see here. And let's do this immediately for all S.
Sorry, can I ask here?
Yes.
But before, could you solve it exactly as S equal to 1 without your like
Yes.
shift interpretation? Okay, so also before.
Yeah,
the
so
end specs.
before, so yes, they could solve it exactly because you can map it to, this Coulomb gas of kink operators. You can write it as some Bose-Nice version of the Kondo model. There's all kinds of ways to describe
so
this
the-
theory. However, the symmetries, there were, there were some issues between the spectrum they found and the correct spectrum of the LRI. I think, but I don't remember where the mismatch was again.
Okay, but this one was with your method. With your
This one
method.
is with our method, and this has all the correct operators that you expect. And I think there were some operators maybe missing from the AYK model if you just take that.
And you were doing again with the Coulomb gas formalism.
So this one is just from taking Neumann boundary conditions of a 2D free scalar, which you can map to the Coulomb gas, etc. Yeah. Okay, so the operators that were listed abstractly in that table, we can make them a bit more precise. So the parity even Z2 even operator with dimension 0 is the identity. That's the first one that we expect. And okay, in the mean field theory, it's also the identity. And then the second operator is an operator with dimension delta over 2 that we expect to be there just from a match with mean field theory. We need a protected operator with this dimension, and this would be the spin field sigma. And we can identify it with the Pauli matrix S3. And I'll come back to that later on. And you can identify it with phi in the phi to the fourth theory. Then the second operator would be chi, that also has protected dimension 1 minus delta over 2. So this is the shadow pair that we saw before. And the operator that matches this one is exactly the derivative of phi. And then we have our scaling operators O plus and O minus. So this is the parity even and Z2 even operator with multiplicity 2 that we saw here. This is exactly the O plus minus that we already saw from the beta function. Now we see here that there should also be an operator, or we find that you can also have an operator that is written in this way. So it's almost the same as this perturbation OG that we saw before, but now with a minus sign in the middle, that has dimension 1 plus delta over 2, and that is odd under both the parity and the Z2 symmetry. And this operator, if we try to match it to phi to the fourth, it would maybe match to d phi, but this is not a conformal primary operator that all these other operators are. It's not it's supposed to be a descendant. So we will need to find a way to show that this also in our theory comes out as a descendant.
And that's also protected?
Yes, and I will show in a minute why. So indeed, this is what I just said. We can identify sigma and chi as the operators with protected dimensions. And chi, okay, I guess no one is complaining about chi, it's just the derivative of phi. But you might complain about sigma because it's a matrix. What's a matrix? Like, how is this an operator? But in 1D, it's important to realize that there's a specific ordering of points that you need to have. There's a path ordering that you need to obey. And sigma 3 in particular does not commute with the sigma plus and minus that we defined in our with our vertex operators. So you can give it effectively a well-defined position just by the fact that if you have it in between a sigma plus and minus and you swap it, it will give some non-trivial contribution. And in that sense, you can define it as an operator, even though it's a Pauli matrix. And okay, it has the right dimensions. There's a shadow pair. And I must say, there's also an alternative way to get rid of this path ordering and of this sigma plus, sigma minus, sigma 3 formalism. You can go to introduce some complex boson and rewrite your whole action. So if you're still a bit uneasy with sigma 3 being some matrix, you could go to this other picture that makes it more well-defined, maybe. Okay, let's now look at this operator that's supposed to be a descendant. And if you and you can see from the quantum numbers that if it's a descendant, it should be a descendant of exactly sigma. But now, okay, we go back to the issue with sigma. If you just take a derivative, you cannot. So how are we going to solve this? Well, we solve it by introducing some covariant derivative, d of x. And this d of x is just the usual derivative plus some commutator with the perturbations of our model. And such a covariant derivative was already introduced in the same way for some magnetic impurity defect. And it's similar to covariant derivatives that you find for Wilson lines, for example. And here it comes from the fact that you have this path ordering and that you have some dependence on the endpoints of your theory that is encoded in this commutator that we find here. So if we define this covariant derivative, we can now apply it to sigma 3 because it has a non-trivial commutation relation with sigma plus and minus. And we find that indeed the derivative is this operator that we wanted to be a descendant. So everything works out and we can map all the low-lying operators to their equivalent operators in the 5 to the 4th theory. So now the last part is to show that this is a one-dimensional CFT, or to provide some motivation for that. And we can do that by using the analytic bootstrap. So what we will do is we will study a set of correlators, either made out of sigma, chi, this scaling operator O plus minus. And from that, since we extract the dimensions for O plus and minus, and also the OPE coefficients that are proportional to the 3-point functions of operators. And we can do this by a means of crossing symmetry in the crossing equation. And the idea for those not familiar is that if you have a correlation function of 4 operators, there's 2 different ways in which you can take the OP. And these 2 ways should be equivalent. And this leads to non-trivial relations, consistency relations on the spectrum and OP coefficients that you can solve. And okay, this is something that we have done. And the nice thing is, and why it is a non-trivial check of our model, is that it only relies on general assumptions and not on the specific form of our model. So what we take as an input is the free model at s equals exactly 1 and delta equals 0, which is this free 2D scalar with Neumann boundary conditions, and the full spectrum that we know from that theory. We also have to assume that these OP coefficients and scaling dimensions go in powers of square root of delta. And we put in that sigma and chi have protected dimension. Then the only other thing that we needed to fix the equations is that there is a symmetry that flips O plus to O minus if you take delta to minus delta. If you don't do this, you get some general relations for O plus and O minus, but you cannot disentangle them in some way. So these are some results that we found for OPE coefficients for sigma, sigma, O plus minus, and sigma chi. And in green is exactly the results that we found if we do conformal perturbation theory of our specific field content. And you see that already at this order, the numbers that you find are not trivial numbers. So the fact that they match is really good evidence that indeed we have a 1D CFT that we are describing. And then with the conformal bootstrap, we were able to to go to even higher orders. And besides this, we have more results also for the full correlators, but okay, that you can find in the paper. And a very nice thing is that there is an additional check that we can do, and that is that there's supposed to be certain relations between these OP coefficients. The exact form is not important, it's just ratios of gamma functions, but there is some specific relations that the OP coefficients need to obey. And they come from the fact that it's a non-local theory, and they were derived for any dimension already some time ago. And in this case, we see that the OP coefficients that we computed agree with these relations. This is a good check again, but it's also a bit surprising because normally we kind of expected that we needed to input these OP relations to get some answers in the analytic bootstrap. But it turns out that if you just take the symmetry of O plus and O minus, that you don't need the OP relations to get the exact answer. And instead you can use it as a check.
So you're satisfying this order by order?
Yes, yeah, you can satisfy it order by order in delta. And they're supposed to hold non-perturbatively, but okay, it's you need to have some starting points. And then on top of that, you can use it to derive new results. For example, the OP coefficients with chi and plus minus, that is otherwise a bit difficult to take, and it saves you having to compute a lot of extra 4-point functions. So these OP relations are very powerful and really are kind of intrinsic to this 1D long-range Ising model. Okay, so let me summarize. So we proposed a weakly coupled field theoretic description for the 1D LRI at the short-range crossover, so close to S star equals 1. And we have an exact solution at S equals 1. And we can do now systematic perturbation theory close to this point. And we can compute beta functions, fixed points, conformal data, everything that you want is on demand. And it matches and extends the results that were already found in the 70s. And we also have the agreement from the bootstrap that shows that we are describing a 1D CFT. So now, what can we do with this? What are the next steps? Well, of course, we can always try to go to higher orders and have further tests of all the things that are intrinsic to the 1D long-range Ising. So we can see if we go further how powerful these OP relations are, if indeed we can kind of get them from the bootstrap instead of needing them as an input. We can see what happens in the middle between the mean field theory description and the one from the short-range Ising side. If there's some hints that maybe it's not a very smooth transition, but something needs to happen. Of course, we can also have some non-perturbative studies, for example, the numerical bootstrap that people are doing. And the perturbative results that we found would form a nice benchmark to see, to compare with numerical results. So then there's an idea of interpreting the long-range Ising model as some theory in ADS2 or as a defect in a free theory in a higher dimensional bulk. And for S equals exactly 1, this is clear. As I said, you can see it as the Neumann boundary condition of a 2D scalar. So it has exactly this defect description of a free theory. But for S smaller than 1, it's not so clear what this would be and how this picture looks like. And so we're trying to see if we can understand how to interpret this. And then maybe also we find some explanation for this symmetry between O plus and O minus, and when we send square root d to minus square root d. So these are some open questions that might be nice to answer. And of course, from this description, you can see if there's other models that might have an alternative description similar to ours. So maybe defect CFTs like this magnetic impurity, or a random field Ising model with long range interactions, or a whole other host of theories that we can think of. So with that, I want to thank all of you, and if you have any more questions, please feel free to ask.
Questions? This ADS and the bootstrap you are talking about,
Yeah.
the project with Gauche, Polish, and Polish, and
Yeah.
this is to use functional.
Yes. Yeah. But numerical. So it's not the analytic bootstrap.
Because it's 1D, so you can probably make use of the analytic.
Exactly. You
functionals
can
and-
do it with analytic functionals. Yes. Yeah. You don't have to go through the usual.
And you
Let's see.
believe the result would be very nice.
Yeah, I have inside information from the Paulos part that no, so I think they already found some nice results, but they want to push it a bit further before they publish it. I don't know the exact status, but yeah.
So the point would be to know better the spectrum for the in between the two regimes.
Exactly. So the idea is that you can see what's going on for intermediate S. So there was so there are some hints if you look at the UV spectrum at the mean field theory side and the short range Ising side. It doesn't really match up well, not in 1D, also not in higher D. So the idea is that maybe something is going on in the middle that's.
So you don't know how to connect the operators in the two regimes.
Yeah, I mean, for the low energy you can, but
Okay.
then in the high energy at some point it seems to behave a bit differently. We haven't really looked into this, but this would be interesting to see. And then numerical results for intermediate S would help with to see what's going on. Yeah, but of course the question is always like, with numerical results, have you found the long range Ising model? So then having the perturbative match on either side is very useful.
Yeah, sure.
Yeah.
Okay, if no more questions, let's.